Welcome, ladies and gentlemen, to the last chapter of your Taylor and Maclaurin series adventure before the AP exam. In today's episode, we will be discussing manipulations of Taylor and Maclaurin series. And in this episode today, we're actually going to be moving a little bit faster than normal because I feel like, we've already kind of discussed how to manipulate some of these. We did some of the examples in the homework a couple nights ago. But before we begin, I do want to warm you guys up with the y equals tan inverse function. We're going to write a Maclaurin series for it. We're going to write the power series function for it using the first four non-zero terms. So in case you're forgetting how to do that, I'm going to get you started. Remember, p of x, since I'm going to center this thing at 0, is going to be f of 0 plus f prime of 0 x plus f double prime of 0 x squared over 2 factorial plus f triple prime of 0 over 3 factorial with an x cubed here plus ... So at this point, I would highly encourage you to pause this video and go ahead, and you're going to need a total of 5 derivatives of tan inverse of x. So 5 iterations of this derivative. Make sure you do them thoroughly, simplify them, because once you get past the first derivative, there's going to be a lot of quotient rule and chain rule happening, and it's going to be pretty nasty. It's going to be the bulk of the problem. So pause the video real quick, please suffer through, and I do mean it, suffer. Find 5 derivatives of this thing, and I will join you in a second. Now that we've suffered enough and have gone through 5 derivatives of inverse tangent, it's time to start making our associations and writing out our power series for tan inverse. And so from here, let's go and write it out. So I've got p of x, so I'll go and switch colors for this one. P of x is equal to f of 0 is going to be tan inverse of 0, which is going to be 0. And I'm going to do this literally and then clean them up in a second here. Plus f prime of 0. Well, f prime of 0 is going to be this guy. So that's going to be 1 x plus f double prime of 0. Well, f double prime of 0 is going to be this guy, but the 0 up top is going to make this whole thing go away, so I don't need to worry about him. So I'll just throw out a 0 right there. And then plus f double prime of 0, well, that's going to be 0 into here is going to get me 0, times, or minus 1 is going to be negative 1. So this will end up becoming actually a negative 2. The 0 down here is going to go to 1, so all I have is 2 over 3 factorial with an x cubed tagging along. So remember, this is f of 0, f prime of 0, f double prime, this is f triple prime, so make sure we keep that in mind. Plus, now we're on the quadruple prime version. The quadruple prime version is going to be 0 because of the x up top, so he'll be 0. And last but not least, we're on the 5th term here, which is the 5th derivative. And so from here, if I let x go to 0, this guy's going to go to 0, this guy's going to go to 0, leaving me with 1. 1 times 24 is straight up 24. But I'm not going to write him as 24. I think you'll know how I'm going to write him down. The 1 plus 0s to the 5th is going to get me 1, so he doesn't really matter. Instead of calling him 24, I'll call him something a little more explicit. I'm going to call him 4 factorial, x to the 5th over 5 factorial. So let's go ahead and clean up our Maclaurin power series here for a second here. So p of x is equal to, looks like x minus, well, this 3 factorial is really 3 times 2 times 1, with the 2's canceling each other out, giving me simply x cubed over 3. This 5 factorial is really 5 times 4 times 3 times 2 times 1, which is really 5 times 4 factorial, which will cancel with the 4 factorial up top, giving me an x to the 5th over 5. And from here, I think a pattern can be established. So I'm thinking my next term, if I wanted to, would be x to the 7th over 7, and since they asked for the first 4 terms, I think we'd be good. Now, obviously, we could find out the next 12 terms if we really wanted to, but this is our power series for tan inverse. So, after all that suffering, I know what you're thinking. So, do I have to go through the derivatives every single time? No, you don't. Of course not. Now, a couple of different options. One, you can memorize the tan inverse power series, which would make your life a little bit easier. But the point of this is how are we able to get to this step here, this step with the final power series? How can we get there without having to suffer through lots of different derivatives? I don't want to do this many derivatives, especially when quotient rules involved. Is there a way that I can extrapolate this particular power series right here in a different way? Well, I think the answer is going to be yes, and it really boils down to the point of the lesson today, which is the manipulation of the Taylor and the Maclaurin series. So I'm going to clean up the board real quick, and then we'll begin the lesson, and we will come back to this power series right here. In fact, I'm going to clip him, and I'm going to keep him. I'm going to take this, keep it, and I'm going to open up its contents when I really need it. So from here, and we'll save him for the end of the episode. We'll save him for the end. We've covered this in passing, in doing some homework. If I wanted you to do y equals x sine x, there were a couple of ways you could have gone about it. You can actually just power through it literally and take 4 derivatives of this thing, in which case you get x cos x plus sine x, and then ... You would get the 4th derivative here being negative 4 cos x minus x sine x. You could do that if you really wanted to, and then literally plug them in to your power series or your Maclaurin series here, just like we did last time, plus ... Now, the shortcut for this was to remember that what you're doing is you are taking a non-polynomial function here, a non-poly, and you are actually multiplying him by, he's linear, but a linear is really just a piece of a polynomial. So because you have a polynomial times a polynomial, you can, or rather a polynomial times a non-polynomial, you can almost treat this polynomial like a constant, where what you can do is you can actually say, all right, if I know that my sine power series is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, then slapping on an x on the outside would be like multiplying this whole thing by x, giving me x squared minus x to the 4th over 3 factorial plus x to the 6th over 5 factorial minus x to the 8th over 7 factorial. Similarly, if I was to give you something like y equals cosine of pi x and ask you to write the power series for that, you would then just have to say, okay, I acknowledge that cosine is going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus ... which would then make cos of pi x, giving us all of our x values in here being replaced by pi x instead. So 1 minus pi x squared over 2 factorial plus pi x to the 4th over 4 factorial minus pi x to the 6th over 6 factorial plus ... So some pretty easy manipulations here, especially when we're just plugging stuff in. While we are on the subject of sine and cosine, let's go ahead and talk about the relationship that they have with each other along with their power series counterparts. So if I look at sine as a power series, and again, I'll just go ahead and write out the first 4 non-zero terms, that way we can see how this happens. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. During one of the classes, I actually had said, hey, if I asked you to find a relationship, and I'm going to write down cosine now, if I asked you to find a relationship between the individual terms here, would you be able to see what the relationship is? In other words, how does the yellow become the red? What mathematical operation needs to happen? Well, from here, any Calc AB student would know that in order to go from yellow to red, in order for sine to become cosine, what you're going to do is you're going to derive sine, and it becomes cosine. But let's see if the Maclaurin counterparts do the exact same thing. Well, if I derive x, do I get 1? I believe I do. If I derive x cubed over 3 factorial, do I in fact get x squared over 2 factorial? Well, let's find out. X cubed over 3 factorial is really 3 times 2 times 1. If I power him down, I would get 3x squared over 3 times 2 times 1. The 3's would cancel each other out, giving me x squared over 2 or 2 factorial. So that checks out. What you're going to find is that this checks out and that this checks out. So by deriving the actual function, you are also deriving the individual pieces of their power series counterparts, which I think is pretty cool. Likewise, if you were to move from the red back to the yellow, the mathematical operation that would make most sense would be integration. And if you integrate cosine, you would get sine back. So if you integrate each of these individual pieces, where you get 1 becoming x, technically x plus c, but you would get x back, this would become x cubed over 3 times 2 factorial, which is really 3 factorial, and down the chain you go. Everywhere where you get a plus c culminates into one big bad plus c at the very end. So anyway, so some pretty good Taylor manipulations and Maclaurin manipulations that we've got here. Likewise, I would encourage you to pause if you want to. Go ahead and derive cosine. And what you'll find is you'll end up getting the negative version of sine, which is what the derivative of cosine is. So just one more way that you can manipulate these so that you can play around with them. Excellent. So I know what you're thinking. After doing all that algebraic manipulation and all the sine, cosine, stuff like that, you're wondering, how does any of this help me with the initial tan inverse problem that we suffered through taking 5 derivatives using quotient rule like crazy people? It's a great question. So in order to do that, I'm going to do something that might actually be equally bad, but I think you guys are going to appreciate this a little bit more. Let's review for a second. When we first started off with Maclaurin series, I gave you a function called this: 1 plus x squared plus x cubed plus x to the 4th plus ... And what we found was that this was a geometric series with a sub 1 being 1 and our ratio being x. And then that meant that our sum was going to be a sub 1 over 1 minus r, which was 1 over 1 minus x. In other words, confirming that this power series here was a representation of this function here. Well, let's talk about this function right here, because what does it look like? Well, this thing, it almost looks like the derivative of inverse tangent, right? This 1 over 1 minus x is almost, actually I'm going to write over here, it's almost 1 over 1 plus x squared. Almost, not quite. So what we're going to do in these next couple steps is we're going to transform our 1 over 1 minus x here into 1 over 1 plus x squared using a series of algebraic manipulations. So what I'm going to do is I'm going to reference this. This is going to be my anchor right here for this example. I'm going to start off with something that looks like this now. Y equals 1 over 1, not minus x, but 1 plus x. All right, so I'm going to slowly but surely transform him into 1 over 1 plus x squared. So what does that get me? That's basically like saying, if you want to look at it a different way, it's looking at it as 1 over 1 minus negative x. And what that allows me to do is it allows me to plug negative x's in for all of these x's up here in my anchor example. So what is that? That's 1 plus negative x squared plus negative x cubed plus negative x to the 4th. After simplifying, I'm going to get 1 minus x plus x squared minus x cubed plus x to the 4th. So I'm one step closer to getting to my tan inverse right here. So what I'm going to do is I'm going to now say, okay, well, cool, let's take him one step further. I'm going to change colors here. Let's call him y equals 1 over 1 plus x squared. So now this guy becomes my baseline for comparison, and all I do is I just take my x's and I square them appropriately. So what I get is 1 minus x squared plus x squared squared minus x cubed squared plus x to the fourth squared. So how does that help me? That gets me 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth. And remember, what I'm saying is that this power series right here is a representation of this function right here. So the last thing I'm going to do, because remember, this power series is a representation of this function. So the last thing I'm going to do is I'm going to integrate this function. And if I integrate 1 over 1 plus x squared, I will get tan inverse of x. But integrating the actual function is like integrating the power series, which would then get me x minus x cubed over 3 plus x to the fifth over 5. And I think this might start looking a little bit familiar, but if it doesn't, it's okay, because we copied that problem from the beginning when we did all of those quotient rules, all 5 of them. We ended up getting this thing. Notice the resemblance. Spitting images of each other, but different colors. So, that is definitely a powerful maneuver for you if you want to keep it in your back pocket so that you can manipulate your power series and your Taylor and Maclaurins. I'll be back with another example. Okay, so in this last example, we will be doing the most difficult one, which is when you have 2 non-polynomials being multiplied. And again, I showed this example once in class, but it's important to note that this one's going to get really, really nasty. So how do we deal with this? Well, what we're going to do is we're going to look at each Maclaurin power series individually. So what I'm going to do is I'm going to say, all right, my e to the x is going to look like this. And then dot, dot, dot. And then my sine x function is going to look like this. And dot, dot, dot. Now there's a couple of options here. I can actually, what I could do, and this would be really, really horrible, is I could actually group them together like this and then FOIL them out. So I could actually just go, okay, u times u times u times u times u times u times u. I could do that, and it would be really, really, really horrible. Or I could do something that you haven't seen in a long time, probably not since your integrated 2 class. I could do an area model on this thing, and when I do an area model, what I'm going to do is I'm going to line up my base times my height, and I'm going to find areas of individual squares. So I'm going to throw my sine version up top, so it's going to be x, and then negative x cubed over 3 factorial, x to the 5th over 5 factorial, x to the 7th over 7 factorial, negative, and I don't think I need to include the x to the 9th over 9 factorial. I think since we're only getting the first 4 non-zero terms, I think that x to the 7th is going to be even too high on its own. So so then I'll just go across, and I'll go and start throwing down my e functions now. So 1, and then x, and then it'll be x squared over 2 factorial, and then x cubed over 3 factorial. I apologize, that should be a 3, and then x to the 4th over 4 factorial. Okay, so from here, what I'm going to do is I'm going to go and find the areas of each individual square. So here, this square, the base is x, the height is 1, so that's going to be x. I'm actually going to call these in a different color here. I'll call these x, and then x times x would be x squared, and then x cubed over 2 factorial, x to the 4th over 3 factorial, x to the 5th over 4 factorial. And then down the chain we go. We'll just go and keep filling these in. I'm going to go and pause for a second, and then fill it in, and then you guys can catch up. And after some lining stuff up, this is what your table should look like. Now notice I didn't complete the table. This would end up becoming x to the 10th and x to the 11th. Honestly, I'm doing the first 4 non-zero terms. I don't think I'm going to need to go that far in terms of how high my degree is going to be. So what I'm going to do is I'm going to go and identify the first 4 non-zero terms. And so let me go and switch to a color here that we can recognize here, lime green. So my first non-zero term would just be x, right? Because it's the smallest power of thing that I have, and I have one of them, right? And so it would be x. And then my next non-zero term, right, would be x squared, right? Because that would be the next power up. And there's nothing else to combine the x squared with. So the x and the x squared really are solo runners here. The next term in my standard power series would be my x cubed terms. And so my x cubed terms, I have to start figuring out which ones of these I have. Well, x I took care of, x squared I took care of. The x cubed is going to have 2 versions, and so I'm going to go and add those together. So I'll go ahead and say plus, I'm going to say x cubed over 2 factorial minus x cubed over 3 factorial. And then I'm going to move on to my x to the 4th. So I'm actually going to move down here. That way I can keep it all on the same deal here. So x to the 4th. So where are my x to the 4th? That's going to be this guy right here and this guy. So x to the 4th over 3 factorial minus x to the 4th over 3 factorial. Now this is a problem because this is going to turn into 0, and I want my first 4 non-zero terms, which means I need to move one more step than I normally would. So that's going to include my x to the 5th values. So x to the 5th is going to be here, here, and here. So I will add those together. So it'll be x to the 5th over 4 factorial. So it's almost exactly like what you guys have been doing in Integrated 2 with the area models, and so now it just has a lot more to it. X to the 5th over 5 factorial. And then if you wanted to simplify this thing, you could call him x. So I'll simplify him over here. Simplify him over on the left side. It would be x plus x squared plus x cubed, and I'd factor out that x cubed, giving me 1 over 2 factorial minus 1 over 3 factorial. And my next term would be x to the 5th, because remember, the x to the 4ths are going to cancel each other away. So I've got x to the 5th, and then I've got 1 over 4 factorial minus 1 over 3 factorial, 2 factorial, plus 1 over 5 factorial. Now, if you wanted to simplify these out, it would end up becoming x plus x squared plus 1/3 x cubed minus 1 over 30th x to the 5th. And that is how you would do that one. Now, again, I don't think that one's going to show up on the AP exam, but it's always good to know how to do all these problems here. Okay, and I think that will wrap it up for this series of Taylor and Maclaurin polynomials. So congratulations on being done with all of the learning that is going to happen before the AP exam. Stay tuned for more videos, and as always, please leave comments and questions in the comments area, and we will see you in the next video.
We should just watch the whole